Okay, so this is help with number 3 on your combination circuit. This is the weirdest one of the bunch, so it's kind of a curveball question. I think these are always the harder of the bunch. So it does look like just a parallel circuit. However, I mean, these two lines are in parallel, but if you look closely, this part right here is behaving in series. So like electricity, here's the positive end. Electricity will come up through here, and your current's going to be flowing here, and then it has a choice. Does it want to go down this route with a 100 ohm resistor? Does it want to go down this route? And when it goes down this route, it doesn't have a choice. It has to go down this one path. So these two guys are acting in series, whereas these two branches are acting in parallel. So when you're going for total resistance, your first step would be to combine these two in series. So you can take this middle step of saying, okay, here's my 10 volt battery, right? And this branch is still 100 ohms, right? Then this branch is equivalent to 150. You don't have to do any fancy 1 over RT. These two are in series. So together, if I were writing it, it would be R2, 1, 2, and it would be 150. So it's the same as if you had one, but the difference is the current through here will be the same, but the voltage is going to drop 2 separate times. So that's where it behaves like a combo problem. Overall, you're right if you were thinking it behaves like a parallel, because it really does, except down this parallel branch, it behaves like a series circuit. So I can now do my total resistance, because this is resistor 3 and this is 1 and 2 kind of together. So your 1 over RT equals 1 over 150 plus 1 over 100, kind of like we do for regular parallel. So you can figure that one out, right? I don't know what that is. And inverse that guy, right? So I'm just doing that. And you get 60 ohms. Okay, so that's your first goal, 60 ohms. Good job. Woot woot. Now you can do good old Ohm's law, find out your total current. So total current, IT, will equal VT over RT. So nothing crazy so far. You kind of always do these steps first. You condense it into one and get the total resistance, then you can use that information with your total volts to get your total current. So 10 divided by 60 is 0.1667, right? That was amps. So I'll use that number most of the time. But for my problem, 166.7 milliamps, since I had to move the decimal place over 3. For the answer, I'm going to put milliamps. Okay, cool. Now is for the part where it gets a little weird. This is where your understanding of the two different types is important, because you have to know that, I'm going to look at this picture because we're going to ignore the fact those are in series. If I just looked at this picture, these two guys are in parallel. So their voltage drops have to be, remember PVC, in parallel voltage is constant. So these two guys have to both drop 10 volts because there's nothing else other than a parallel circuit at this point. So it's going to drop 10 volts here and drop 10 volts here. Now that's cool and all, but it doesn't really help you here, because remember how some of your 10 volts will drop there and some will drop there? But it does help for R3, because down this branch, the whole branch, it'll drop 10 volts. So the voltage on resistor 3, which is this guy, is a 10 volt drop. You don't know yet here, but I know their total will be 10, right? All the way down. But now you kind of opened up the world here, because as soon as I know this, I can figure out its neighbor. As soon as I know this, I can figure out its neighbor, sort of thing. So if I know the voltage on 3, and I know the resistor on 3, I can figure out the current on 3. So you kind of go through here. You say I3 is going to equal V3 over R3. Okay, what's my voltage on 3? We just figured that out. It's 10 volts because PVC. And then R3 is 100 ohms. Okay, and we don't really need a calculator on this one, right? But, just being safe if you want, it's 0.1. Okay, add some zeros if it helps you go 1, 2, 3. Also known as 100 amps. Okay, cool. How does that help me? This is why this problem's kind of hard. I much prefer the other two on the other side. But on this one, now that I know that's 100 amps, sorry, oh, that's milliamps, jeez. Now that I know that's 100 milliamps, I know that, remember how circuits with parallel, part of the current goes down this branch and part of the current will go down that branch, but it's got to add up to the total current? Because when this problem starts off, you have 166.7 milliamps coming out of here. Then when I go down this branch, if I used 100 milliamps, I already know that down this branch, I have 66.7 milliamps. Now, why do I have them both at 66.7? Because these two guys are in series. And in series, current is constant. This is a tough problem. If you struggled on this, totally understand why. Now that you know these two, you can figure out these two with good old Ohm's law. All right, I'll leave that up to you. Give it a whirl. Hopefully that made sense. There is another way to do this, but I'm going to not do that right now. So I'll show you a different way in class if you want to see it. It's just different. I think this way is pretty cool because it brings up some old ideas. Hopefully that helps you get unstuck on number 3 if you were stuck on it. All right, there you go.